Thank you. Okay, and now the opposite is true if we marginalize over C. Then A and B become dependent if we marginalize over C, and this one, if we marginalize over C, average out over C, A and B get independent in the case of a collider. It's just the opposite. Huh? This is marginalizing has averaging over this one, summing over C, then those get dependent, and that one gets independent. It's just something you might remember, that even if it seems here that they're independent, if I condition on C, they get dependent. That's probably the most important thing you have to take here from this transparency. Okay. So that's called a collider. And if it's not like that, it's called a non-collider if it has only one incoming error. Then it's a non-collider. Okay. So, this is the summary of what I've told so far. Actually, belief networks, they correspond or can be represented by directed acyclic graphs, and they represent or display the conditional independence assumptions that I have in this model. So they show actually the minimum way to factorize out a joint probability distribution, and this can display best in a directed acyclic graph. Good. Now we come to Bayes' rule, and we look at it not now with x and y, but what we normally have instead of x and y, we have probably a set of parameters of our learner given some data. And now we can calculate how probable is the model given that data. Is it a good model for this kind of data? To answer that question, we have to use Bayes' rule. Then we have to calculate the probability that this data would be generated given the parameters times the prime probability of the parameters. We can assume some distribution over these parameters because these are random variables as well, over the evidence. That's called the evidence. It's a marginal over all the thetas here, over all possible distributions of the parameters. That's how in machine learning we would read Bayes' rule and mostly apply it to. So we have actually x and y get, for example, here parameters or a model given a data set, given a sample. Okay, it was Reverend Thomas Bayes who first actually wrote about this theorem. So it was a reverend, a priest, and just to name the thing here, instead of, for example, a parameter vector theta, we could generalize it to a hypothesis. A hypothesis could also just represent a kind of a learner that we select. We select out of a hypothesis space a given learner. Let's say, okay, let's try random forest. This would be a hypothesis already we put in here. Often we don't use this P of x because this is mainly just a normalization factor, and we just can compare actually the denominator for different values of h and then choose the most probable one just by relative comparison of these two things. This is called the likelihood of the data given the model or the hypothesis H, and it is normally not normalized, so we call it the likelihood function. It's not a probability density. So it's called the likelihood function. And only by normalizing by these two factors, the whole thing gets, again, probability distribution. But sometimes it's not necessary to have it normalized. We just compare different likelihoods. Okay. So, naming, again, we would say this is the likelihood function because it's not a probability density distribution. This is the prior know-how, our expert know-how that we put already into our learners. And this helps to improve actually a prediction if we make the right assumptions. If we just make here a flat assumption, so a uniform distribution over the theta, then we know no other than just the likelihood here. So if P from theta is just uniform over the whole space of possible thetas, we don't really make use of base null. We're making actually a null assumption over the theta distribution. But as soon as we know something about this here, it will get better. It will get better and better, because we can also, if we have new data, just apply this rule to improve our know-how about this. So we can use actually this formula as an update rule for new data as well. Good, okay. There are two main things that we can do, and the Bayesian world would actually stick to that one. The maximum a posteriori distribution, which is giving us the maximum over the full distribution, over this here nominator, including the prior. This is called the maximum a posteriori, because this is the posterior distribution, and we want to maximize that one. Sometimes we're just happy with maximizing the likelihood function, and then we call this the maximum likelihood assignment. This is easier to calculate than that one, because here I have to integrate through. I have to multiply, I have to marginalize. This is harder work. This is easier, and sometimes it's even easier because we can take not only the likelihood function, but the logarithm of the likelihood function. And why the logarithm? By the logarithm, it's a monotonous function. We get just out actually the argument of the exponential function, the Mahalanobis distance. And this is now a linear or quadratic function. Makes it much, much easier. These are the main two things that normally are done to estimate actually, or even set, for example, of parameters. And we call this the maximum likelihood estimate, and this is the maximum a posteriori estimate. What is the difference here? This is a point estimate. So we get just one value for this vector of thetas. And we don't know how it is distributed. A Bayesian statistician would say, let's do that one, because then we get the full distribution over the parameters that we have estimated. It's not just a point estimate, we get out the full distribution, so we can give a probability how probable it will be that this parameter set is the correct one. We can assign that, but we cannot do that here because it's a point estimate. We're just maximizing the function, given here at this point we have the maximum. But using the prior knowledge, actually we still get a distribution as output out of Bayes' rule. That's a big difference. We get the distribution at once without having to sample over 1,000 samples over this test case. So we could do that by bootstrapping and just say how are the thetas distributed, or we can do it in a Bayesian way by giving here the prior know-how about the distribution of the thetas as prior information in. Okay, now I would say for us the most important application is the naive Bayes classifier. Whoever has heard from that one, some of you, Bayes classification is quite a good classifier, and it makes one important assumption, namely that actually all features are independent on each other, which means that we can factorize out the probability distributions easily, and then we can reverse it. So, assume Y is a label of a class. We want to know whether it's male or female. We measure some size of a fish, the width, the height, the weight. We want to know, given something, is it male or is it female? So this would be the label. Given these features, weight, size, and width. Then using Bayes theory, we can revert that, because normally we have the probability of the x given the y. And then we can reverse it, and Bayes, the naive Bayes assumption is that all these x are independent of each other. So we can multiply that out. There are no conditional dependency anymore, and this gets actually the product of all features given that class, given that male or female. And this we normally get out of a table, out of a frequency table, out of the data we have measured. We can calculate this. This is just a number. And we have to sort it out. We have to look at class 1 and say, how frequent is the length 1.2 meter? How frequent is this, and so on. And then by multiplying here, this is the prior, what is the probability that it is male at all? Because in this sample, probably we had 15 males and only 2 females. Then we have to take this into account. And this is given then by here, this marginal distribution over y, over the sex of the fishes. And then we can make an argument. We can say, if I have now unseen data, a new distance, a new length, a new width, a new weight that I've never seen before, we can calculate the probability that this is now a male fish or a female fish by using exactly only this nominator. And we don't calculate the probability, but only actually the denominator, which is not normalized, but it's sufficient because we do it for all the classes, and then we take the maximum value of this. So if this is 10 to the minus 6, and for the female it's 10 to the minus 4, then we say, okay, then it's female. Because the probability is high, because for both of these classes, here we average over all the classes. This denominator is the same. We'll make an example in the exercises, in the practice, where we have just given a table and we have to sort out what is the probability of y given x, or what is the probability of x given y. Knife base, and it's quite a good classifier. We had looked at it in the learning curves, at the beginning. It makes no assumptions except these dependency assumptions. We don't need any parameter, nothing. We estimate actually the probability distribution of the x by assuming all the x are independent. That's it. It's called the knife-based classifier. It's quite a good one. Good. Just to say, okay, what is the difference between looking at the world in a frequentist glasses, with using frequentist glasses, and Bayesian glasses, probability glasses, for example? A frequentist would say, if I observe with 10 coin, how do you call this? Coin experiments, tosses, coin tosses. I observe 3 heads out of 10. What is the probability then to observe head? It would be 3 of 10. It's quite simple. But if a Bayesian would look at this like that. He would calculate the likelihood function. What is the likelihood to observe such a sequence? And he would put up actually binomials distribution and say, okay, 3 of 10 is theta to the power of 3, 1 minus theta to the power of 7. We maximize that. We take the maximum likelihood over this distribution, 10 over 3. This is not important because it's a constant. The log, the likelihood is then 3 log theta plus 7 log theta, 1 minus theta. We put this to 0, the derivative to 0. This is the maximization of the likelihood, and then we get the maximum likelihood estimate of our theta. And it turns out to be the same. Right? It's also 3 over 10. 3 over 10. But that's the way how we would look at it in a probabilistic way, not in a frequentist way. Right? Of course, for this simple example, I agree, it's easier just to count, but later probably we have to go this way. We have to take the derivative of the log likelihood to find the maximum likelihood estimate. Okay, for a Gaussian, let's do it now for a Gaussian. Here we cannot count anymore because it's a continuous distribution. What is the maximum likelihood estimate of a Gaussian distribution, for example, for the maximum likelihood distribution or estimate for the mean and the variance? How do we calculate that? If we take the log likelihood, actually, we just get the argument out, and all the constants they get to sums here and they are not important. These are the normalizing factors. And what only remains is kind of this Mahalanobis distance. Taking the logarithm of this multivariate Gaussian just gives us the argument out of the exponential function. And now we can calculate, okay, the logarithm we have taken, we divide it over mu because we want to get a maximum likelihood estimate for the mean. And what we get out is this here, it's a linear function, and we see, okay, exactly, the maximum likelihood estimate for the mean is exactly the sample mean. For you this is clear, but it's actually not that clear at the beginning, because for the variance it's different. So we would say the sample mean is clear, it's the average over all samples examined over the sample size. But the variance, you know, the formula for the variance has an n-1 in it. So the variance is not calculated by the sum 1 over n x minus mu squared. It's 1 over n-1. And where does this n-1 come from? It comes from the maximum likelihood estimate. Just to explain it, this one here is n-1. If we derive actually now for the sigma, the maximum likelihood estimate for the variance, we get an n-1. That's just an explanation why in this formula, for the estimate, for the variance here, is a factor n-1, 1 over n-1, because it's the maximum likelihood estimate. And this is an unbiased estimator. It converges for big n's really to the real variance. And if I take only an n, then it's biased. It has a certain offset for small n's, which I don't get out. So it means a maximum likelihood estimate is already better than the thing we would say it's normally, it's just an average over n. No, the maximum likelihood is even better. It's biased, not biased, it's bias free. Okay, this is an example. If we have time in the exercises, we'll also do Bayesian inference for a Gaussian. And what does it mean? Now, what happens if we put as a prior distribution also a Gaussian distribution, for example, also over parameters? Then it turns out that we again get a Gaussian distribution, but with different variance. And the variance is an additive, so these two things add. And we will see how, for example, noise gets into this Gaussian distribution, how it is added. This we'll do in the exercises. Good. But the main thing is actually, if we put a prior, which is at the beginning very, very broad, and we do iteratively maximum likelihood estimation, we will see as the number of samples gets up, actually we get a narrower distribution over our, for example, the mean. And at the end, it centers really at the real mean with a very narrow peak. And that's a bit how this how the Bayes rule applies to it. So we put our prior knowledge into the prior distributions, and what it means, it narrows down the distribution over the estimates that we do using that. And it continuously gets narrower until it converges here, in this case, to the real variance of the real mean. Good. Gaussian mixture models. We looked at it last week a little bit. For example, I told you that we could do speaker identification by modeling a speaker's voice as, or the capsule coefficients as a mixture of Gaussians. So we have seen this complicated transformation of a time series, of a wave data file, for example, into these frequency bands, and applying then the cosine transform to get these capsule components, the Mel capsule frequency components. If you look at the distribution of these frequency components, we see, okay, they're quite smooth, and they're characteristic for a speaker. So we can model actually a speaker by using multivariate Gaussian distributions for these capsule components over a certain time. Would mean we listen to a speaker, for example, for 20 seconds, calculate the Mel capsule frequency components, make a histogram for each of these 13 bands that we said are relevant, and then we fit Gaussians to these distributions in these 13 bands. And then we store the means and the variances of all these Gaussians and say, this represents this speaker's voice. And later, we can match the thing for an unheard voice, for a new test, for example. We would say, okay, where we have the best match? Where's the maximum likelihood here for this given voice? Which speaker is most probable? This is a maximum likelihood problem. And we look at a really nice algorithm. It's called the expectation maximization algorithm. And it mainly does what we did before. It's kind of a Bayesian inference in 2 steps. It's a special case. And it's an iterative algorithm where we do actually an update of certain variables, and using these updated variables, we make an update on the assumptions, for example, for different values. Okay, that's how a Gaussian mixture model looks like, for example, in 1 dimension. This would be the true distribution here. And we would see, okay, it could be modeled as a superposition, means a sum of 3 independent Gaussian distributions with certain means and certain variances. That's a 1-dimensional Gaussian mixture model. Now you can imagine for the speaker identification, this is the distribution over the capsule coefficients at a certain frequency band. And this is speaker specific. And if we model this distribution by a sum of Gaussians and store only the means, the variances of this Gaussian distribution, it's a representation of the sound utterances of this voice. And we do this for all these 13 bands. This is what we will do at the end to apply it. Good. Yeah. Given some sort of sample distributions, we can also say, okay, we can approximate it by a superposition of many multivariate Gaussian distributions. And this is shown here, animated a little bit, you see? Okay, then I can, this experimental distribution, I can fit using 2 independent multivariate Gaussian distribution. This is now a 2-dimensional Gaussian mixture model where I have 2 independent random variables. And I set it together with 2. I could also use 3 or 4. This depends on the problem given. But normally, our assumption is then the distributions are very smooth. The Gaussian distribution is really a very smooth distribution, so we average out certain things. Very peaky things would have to be distributed or modeled by a 3rd distribution, which is very narrow. And the parameters are the means and the variances of these. Okay, how does it work? I explain it already with the next slide here. Let's assume we want to really identify, for example, the voice of a speaker. Or we could also say the sex of a speaker. What is the gender? Is it male or female? Then we have only 2 classes. Our goal is actually we listen to somebody and the output should be male or female. How can we do that? We have stored actually our features, our Gaussian distributions of the voice features for each male, female speaker. What we do first, we say, okay, we can model it, let's say, assuming some Gaussian distribution centered at random spaces here at the mu k using random variances sigma k. And let's say we do this using D distributions, 5 for example. And they're fully unknown. And we also don't know whether now this speech signal that we have comes from a man or a woman. But what he then calculates is actually the probability that these features come from a man or a woman. And we do it for both kind of classes. And we assume actually that these features are distributed like a Gaussian. So the likelihood is given by the distance of being male or female over this distribution centered at the mu. Normalized over all these distributions for 2 classes. The classes are hidden. We don't know it at the beginning. Huh? But now I can assign actually a likelihood here, or a probability that they belong to a man or a female. This was done using random at the beginning. Random variances, random mean vectors. Now the second step is we make an update. We calculate now better estimates for our mean values and the variances. And we do this just by averaging over the probabilities that we have just calculated. So we can calculate just the mean by taking the first moment over these distributions. We calculate the mean given this probability distribution. This gives the mean for example, this first class, the second class. And now we have updated things which are fitting better to the redistribution, and we repeat it until it converges. And depending on the initialization that I make, it will converge. Every initialization is a little bit different, so it doesn't converge as easily to the same thing. And what I could do is actually using, first of all, a clustering algorithm to assign, for example, already certain classes to given thing, and then using centroids to put actually the means and the variances already at these points. This would be a better initialization. But at the beginning, we just start actually with two random variables. So there's an E step and an M step, an expectation step and a maximization step here. Okay. That's it. Let's see how we would apply it now to this voice recognition system. You remember, for example, this was the paper from Reynolds and Rose. We had calculated this capsule coefficient. And how do they look like? They do not look like this, they look probably like that. Let's assume now this is the histogram of the capsule components, the male capsule components at a given frequency band. And you see here from this distribution, this is similar to actually a superposition of 2 or 3 Gaussian. And this was exactly the idea that Reynolds used and said, let's model this as a Gaussian mixer model here. Right? Not a similar Gaussian, but the superposition of 3 Gaussians. What is shown here, this would be a vector quantization approach where we say, okay, we assume only discrete values here over this distribution and just say, okay, what is the most frequency within these discrete values of quantized values. But here, actually, for each speaker and for each frequency band, we have some components which are given by mu, the variance, and the number of Gaussian distributions we use to approximate this distribution. And we have this in 13 bands, and that's what he did. And this is stored, and actually these mean values for every speaker, and I think he looked at 49 speakers. For every band, they're stored and represent actually this speaker's voice. Now we turn it around and make a maximum likelihood estimate to identify the speaker. So we turn it around. And we do it the same thing, it's maximum likelihood. He makes additional assumptions that actually these things are independent, so he models it just with one-dimensional Gaussians, not multivariate Gaussians, so it makes it a little bit more simple, uses a univariate Gaussian distribution to calculate here the probability that this voice belongs actually to speaker I. And at the end, actually, we can use, okay, what is the probability of the speaker being Y? Here, that's here. This is the Gaussian, the expectation maximization, again, now with this distributions given. What is the probability that, given these features that we measure out of the capsule components, it is speaker I out of these 49 speakers. We made the average over these Gaussian distributions, the Gaussian distributions over all these bands, calculate this probability, and then we average out the weights, the mu and the sigma, train it again iteratively using the maximum, the expectation maximization algorithm to calculate the maximum probability over this I. And we take the maximum value of these probabilities to identify this speaker's voice. Yeah. So that's it. It's probably good to have a look at this paper to see the details of it, how he did it. It's quite an old paper, 95, using these capsule components and how he set up really the probability distribution over these capsule components. So it's feature generation inside, then modeling these features using Gaussian mixture models, and using expectation maximization algorithm to learn these distributions out of the speak samples he had. And later apply a maximum likelihood estimate to identify the speak loss. That's one example of how to apply actually Gaussian mixture models combined with maximum likelihood estimate to identify a speaker's voice. Good. I think that's more or less what I wanted to tell you today. Are there any questions? Good. Then I would say we start at 4 o'clock with the practice. Good.